Welcome to this comprehensive lesson on artificial intelligence in cybersecurity. Today, we'll explore the fundamental concepts of AI and discover how they're revolutionizing the way we protect digital assets and combat cyber threats. Artificial intelligence in cybersecurity represents a paradigm shift in how we approach digital defense. AI enables computers to learn from data patterns, detect anomalies automatically, respond to threats in real time, and adapt to new attack methods. AI is being applied across multiple domains in cybersecurity, from faster threat detection and phishing prevention to behavioral analytics and network security. AI technologies are transforming how organizations protect themselves against cyber attacks. Throughout this course, we'll explore three fundamental types of machine learning. Supervised learning uses labeled examples to make predictions, like detecting spam emails. Unsupervised learning finds hidden patterns in data without labels, perfect for anomaly detection. Reinforcement learning adapts through trial and error, enabling dynamic defense systems. Modern cyber threats form complex networks of interconnected actors and attack vectors. Traditional security methods struggle to keep pace with this complexity. This is where AI becomes essential, helping us understand, predict, and defend against sophisticated attack networks in real time. In this comprehensive course, you'll master core machine learning algorithms and their cybersecurity applications. We'll cover data preprocessing, model training, and explore real-world use cases. You'll also learn about AI's challenges and future potential. By the end, you'll have a solid understanding of how AI is transforming cybersecurity and protecting our digital world. Let's begin this exciting journey into the world of AI-powered cybersecurity. Our first stop will be understanding what machine learning really means and how it applies to digital defense. Machine learning, or ML, is a subset of artificial intelligence, where computers learn patterns from data without being explicitly programmed for every single task. To understand this better, let's compare traditional programming with machine learning. In traditional programming, we write explicit instructions for every possible scenario. In contrast, machine learning takes a fundamentally different approach. Instead of explicit programming, we provide data and let the algorithm discover patterns and learn from examples. The key insight is that machine learning algorithms discover patterns automatically. They analyze examples, identify relationships, and build models that can make predictions on new, unseen data. This fundamental difference makes machine learning incredibly powerful for cybersecurity, where new threats emerge constantly and explicit programming for every possible attack would be impossible. Machine learning plays a crucial role in modern cybersecurity by transforming how we detect and respond to cyber threats. Cyber threats are constantly evolving and becoming more sophisticated. Attackers develop new techniques, exploit zero-day vulnerabilities, and adapt their methods to bypass traditional security measures. Traditional security methods rely on predefined rules and known attack signatures. While effective against known threats, they struggle with new, unknown attacks and cannot adapt quickly to evolving tactics. Machine learning offers a revolutionary approach to cybersecurity. Instead of relying on predefined rules, ML algorithms learn from data to identify patterns and detect threats automatically. ML employs various sophisticated algorithms for anomaly detection, each designed to identify different types of unusual behavior and potential security threats. Machine learning algorithms analyze vast amounts of historical security data, including attack logs, network traffic patterns, user behaviors, and system events, to learn what normal and malicious activities look like. Unlike reactive traditional methods, machine learning enables proactive cybersecurity defense. ML systems continuously monitor network activity, analyze patterns in real time, and can detect and respond to threats before they cause significant damage. Machine learning transforms cybersecurity by detecting previously unknown threats, adapting to new attack methods, reducing false alarms, enabling real-time automated responses, and scaling effectively with increasing data volumes. This makes ML an essential component of modern cybersecurity defense strategies. In summary, machine learning is not just helpful but crucial for modern cybersecurity, providing the intelligence and adaptability needed to defend against today's sophisticated and ever-evolving cyber threats. Supervised learning is a fundamental type of machine learning where we train models using labeled data. This means we provide the algorithm with input examples that already have known, correct outputs. Let's understand this concept using a practical example. Imagine we want to teach a computer to recognize different types of vegetables. We start with a collection of labeled training data. In supervised learning, each input in our training data comes with its correct label or output. Here we see carrots labeled as carrots, tomatoes labeled as tomatoes, and bell peppers labeled as bell peppers. The model learns by studying these input-output pairs. It identifies patterns and features that distinguish one vegetable from another, such as shape, color, and texture characteristics. After training on many labeled examples, the model can then make predictions on new, unseen data. It applies the patterns it learned to classify new vegetables correctly. The key characteristic of supervised learning is this input-output mapping. The model learns to associate specific input features with their corresponding correct outputs, enabling it to make accurate predictions on new data. This supervised approach is widely used in cybersecurity applications such as spam detection, malware classification, and intrusion detection, where we have historical data with known classifications to train our models. Spam detection is one of the most common and practical examples of supervised learning in cybersecurity. Email systems process millions of messages daily, and distinguishing between legitimate emails and spam is crucial for security. The challenge is straightforward. Given an incoming email, we need to automatically classify it as either spam or legitimate mail, also called ham. In supervised learning, we start with labeled training data. Here we have examples of both spam emails, which contain urgent language and suspicious senders, and legitimate emails with normal business communication. A real spam detection system trains on thousands or millions of labeled email examples, learning patterns that distinguish spam from legitimate messages. The next step is feature extraction. The algorithm identifies key characteristics in emails that help distinguish spam from legitimate messages. The system extracts various features from emails: suspicious keywords, sender information, email structure, formatting patterns, and the presence of links or attachments. Now let's see how this process works in practice with a visual representation of the spam detection system. This diagram shows the complete spam detection process. Incoming emails are analyzed by the machine learning system, which has learned to categorize them based on the training data. The brain and chip represent the trained machine learning model that has learned from thousands of examples. When new emails arrive, the system applies this learned knowledge to classify them as ham or spam. Let's see how this supervised learning approach works when classifying a new, unseen email. Here's a new email with suspicious characteristics: urgent language, promises of free items, and a promotional sender address. The trained model analyzes the email's features and compares them to patterns learned during training. Based on the learned patterns, the model classifies this email as spam with high confidence, demonstrating how supervised learning enables automatic threat detection in cybersecurity. This demonstrates the core principle of supervised learning. The system learns from labeled training examples to make accurate predictions on new, previously unseen data. Unsupervised learning is fundamentally different from supervised learning. In unsupervised learning, we work with unlabeled data, meaning we don't have the correct answers or target outputs provided to us. Let's visualize this with an example. Here we have a collection of data points scattered across our space. Notice that these points have no labels, no categories, and no target values assigned to them. The goal of unsupervised learning is for the algorithm to discover hidden patterns and structures within this data. The model must identify inherent groupings or relationships without any guidance about what the correct answer should be. Watch as the unsupervised learning algorithm analyzes the data and begins to identify natural clusters. It groups similar data points together based on their characteristics and proximity, revealing the underlying structure. The algorithm has successfully identified 3 distinct clusters in our data. Each cluster represents a group of similar data points that the model discovered on its own, without being told how many groups to find or what characteristics define each group. This process of pattern discovery is what makes unsupervised learning so powerful in cybersecurity. It can identify unusual network behavior, detect anomalies in system logs, or discover new types of threats that have never been seen before. Unlike supervised learning, where we train models with correct answers, unsupervised learning algorithms must be exploratory detectives, uncovering relationships and structures that weren't obvious at first glance. This ability to find patterns in unlabeled data makes unsupervised learning essential for cybersecurity applications where new and unknown threats constantly emerge. In cybersecurity, anomaly detection uses unsupervised learning to identify suspicious network activity without prior knowledge of specific attack types. The system learns what normal behavior looks like and flags anything that deviates significantly from this baseline. First, the unsupervised learning algorithm observes normal network traffic patterns. It analyzes data points like IP addresses, packet sizes, connection frequencies, and timing patterns to establish a baseline of typical behavior. This visualization shows how network traffic data is analyzed. The heat maps display IP address distributions, while the variance graphs below track changes in traffic patterns over time. The green lines mark points where significant deviations occur. When new network traffic is analyzed, the algorithm compares it against the learned baseline. Normal traffic patterns, shown in blue, fall within expected parameters. However, anomalous activities, highlighted in red, deviate significantly from the established normal behavior. The system automatically flags these anomalies for further investigation. This could indicate potential security threats like unusual data transfers, suspicious connection patterns, or unauthorized access attempts that don't match typical network behavior. The key advantage of this unsupervised approach is that it doesn't require prior knowledge of specific attack signatures or patterns. It can detect previously unknown threats by simply identifying behavior that deviates from the established normal baseline, making it particularly effective against zero-day attacks and novel threat vectors. Reinforcement learning is the third major type of machine learning. Unlike supervised and unsupervised learning, reinforcement learning involves an agent that learns through trial and error by interacting with an environment. Here we have a simple environment where an agent must learn to navigate from the starting position to reach a goal. The agent doesn't know the optimal path initially and must discover it through exploration. Reinforcement learning has 5 key components. The agent is the learner that takes actions. The environment is the world the agent interacts with. Actions are the choices available to the agent. Rewards provide feedback on how good each action was. And the policy is the strategy the agent develops over time. The agent learns through trial and error. In each episode, it tries different actions and receives rewards or penalties based on the outcomes. Let's watch the agent explore and learn. Over many episodes, the agent adapts its strategy to maximize rewards. It starts with random exploration but gradually develops a policy that avoids obstacles and seeks rewards. The goal is to maximize cumulative rewards over time, not just immediate rewards. This ability to learn optimal strategies through trial and error makes reinforcement learning particularly powerful for dynamic environments where the best action depends on the current situation and long-term consequences. In cybersecurity, reinforcement learning enables AI agents to adapt their defensive strategies dynamically in response to evolving attack patterns. This creates intelligent defense systems that learn and improve over time. The AI defense agent operates within the network environment, continuously monitoring for threats and making decisions about how to respond to potential attacks. The reinforcement learning process involves the agent taking actions within the network environment. These actions might include blocking suspicious IP addresses, increasing monitoring levels, updating firewall rules, or isolating compromised systems. The agent receives rewards or penalties based on the outcomes of its actions. Successful threat blocking earns positive rewards, while missed attacks or system disruptions result in negative rewards. This feedback helps the agent learn optimal strategies. This creates a continuous learning cycle. The agent takes an action, observes the outcome, receives feedback in the form of rewards or penalties, and then adjusts its strategy accordingly. Over time, the agent's performance improves dramatically. Initially, it may take random defensive actions with limited success. As it learns from experience, it begins to identify attack patterns and improve response times. Eventually, the agent develops sophisticated, proactive defense strategies that can anticipate and counter new types of attacks. This adaptive capability makes reinforcement learning particularly valuable for cybersecurity, where threats constantly evolve. Machine learning algorithms form the backbone of AI-powered cybersecurity systems. Today, we'll explore two fundamental regression algorithms that are widely used in security applications. Linear regression is a fundamental algorithm that predicts numeric values by finding the best fit line through data points. It's particularly useful when we need to estimate continuous quantities. Here's how linear regression works in cybersecurity. Imagine we're tracking attack risk scores over time. Each blue dot represents a data point showing the risk level on different days. Linear regression finds the best fit line through these points. This red line represents our predictive model that can estimate future attack risk scores based on the trend in our data. For example, we can predict that on day 9, the attack risk score will be approximately 8.0. This helps cybersecurity teams prepare for potential threats before they occur. Logistic regression is different from linear regression. Instead of predicting numeric values, it predicts categories by calculating probabilities between 0 and 1. In cybersecurity, logistic regression helps classify files as malicious or benign. The x-axis shows a file's suspicion score, while the y-axis shows the probability it's malicious. The red S-shaped curve is our logistic regression model. Green dots represent benign files with low suspicion scores and low malicious probabilities. Red dots represent malicious files with high suspicion scores and high malicious probabilities. The yellow dashed line at 0.5 probability is our decision threshold. Files above this line are classified as malicious, while files below are classified as benign. Regression algorithms can also work with multiple variables simultaneously. This 3D visualization shows how multiple factors can be combined to make more accurate predictions in complex cybersecurity scenarios. Regression algorithms are essential tools in cybersecurity AI systems. Linear regression helps predict when attacks might occur, while logistic regression classifies threats. Both learn from historical data to enable proactive security measures. Decision trees and random forest are powerful machine learning algorithms that excel at making classification decisions through a series of logical questions and branches. A decision tree works by asking a series of yes or no questions about the data. Each question creates a branch that splits the data into smaller, more specific groups. In cybersecurity, decision trees can classify threats by examining file characteristics. For example, they might ask about file size, network access permissions, or encryption status to determine if a file is malware or safe. When analyzing a new file, the decision tree follows a specific path. A large file with network access might be classified as malware, while a small encrypted file could be deemed safe. While a single decision tree is useful, it can sometimes make errors or be too specific to the training data. This is where random forest comes in. Random forest is an ensemble method that combines multiple decision trees to make more accurate predictions. Instead of relying on just one tree, it creates a forest of many trees. Each tree in the random forest is trained on a slightly different subset of the data and uses different features. This diversity helps reduce errors and improves overall accuracy. When classifying a new threat, each tree in the random forest makes its own prediction. The final decision is made by majority vote. In this example, 3 trees vote malware and 2 vote safe, so the final classification is malware. This voting mechanism makes random forest more robust and accurate than individual decision trees, significantly improving threat detection in cybersecurity applications. This visualization shows multiple decision tree structures, each with different branching patterns and decision paths. In random forest, this diversity of tree structures contributes to more accurate and reliable threat classification in cybersecurity systems. Decision trees provide clear, interpretable rules for threat classification, while random forest improves accuracy through ensemble voting. Both algorithms are robust against overfitting and provide fast predictions suitable for real-time cybersecurity applications. Two essential machine learning algorithms stand out for their effectiveness in cybersecurity applications: k-nearest neighbors and support vector machines. Each uses a different approach to classify data and detect threats. K-nearest neighbors works by finding similarities between data points. When classifying a new sample, it looks at the k closest neighbors and assigns the most common category among them. This visualization shows how KNN classifies a new blue data point. By examining its nearest neighbors, the algorithm determines it belongs to category A, changing its classification accordingly. In cybersecurity, KNN excels at clustering similar malware samples. By comparing file characteristics, behavior patterns, and code signatures, it can group related threats together, helping security analysts understand attack families and variants. Support vector machines take a different approach by creating optimal boundaries called hyperplanes to separate different categories. The algorithm finds the boundary that maximizes the margin between classes. This visualization demonstrates how SVM creates hyperplanes to separate data. In 2 dimensions, the hyperplane is a line separating green circles from red squares. In 3 dimensions, it becomes a plane that divides the data space. In cybersecurity, SVM excels at binary classification tasks like distinguishing malicious from safe behavior. It analyzes network traffic patterns, file characteristics, and system activities to create clear decision boundaries between threats and legitimate operations. Both algorithms serve different but complementary roles in cybersecurity. KNN excels at finding similarities and grouping related threats, while SVM creates clear decision boundaries for classification tasks. Together, they provide powerful tools for detecting and analyzing cyber threats. Overfitting is one of the most critical problems in machine learning that can severely impact cybersecurity systems. Understanding this concept is essential for building reliable AI-powered security solutions. Overfitting occurs when a machine learning model becomes too specialized to its training data. Instead of learning general patterns that apply to new situations, the model memorizes specific details from the training examples. This visualization shows 3 different levels of model complexity. The left shows underfitting with a too simple model, the middle shows appropriate fitting, and the right shows overfitting, where the model follows every detail of the training data. Notice how the overfitted model on the right creates a complex curve that passes through every training point. While this looks impressive on training data, it will likely fail when encountering new data points. This graph demonstrates the classic signs of overfitting. The blue line shows training performance continuing to improve, while the orange line shows test performance plateauing or even decreasing. This gap indicates the model is memorizing rather than learning. In cybersecurity, overfitting poses a particularly serious threat. This network visualization shows the complex and evolving nature of cyber threats over time. Cybersecurity faces unique challenges with overfitting. New threats constantly emerge that differ from historical patterns. Attackers continuously evolve their methods, and an overfitted model that memorized old attack signatures will miss these novel attack vectors. This is the critical danger. An overfitted cybersecurity model becomes a liability, creating blind spots that attackers can exploit. The model's overconfidence in memorized patterns makes it vulnerable to new unseen threats. Remember, overfitting means memorization without generalization. In cybersecurity, this creates dangerous vulnerabilities where AI systems fail precisely when they're needed most, against new and evolving threats. Underfitting is a critical model error that occurs when a machine learning model is too simple to capture the underlying patterns in the data. This simplicity can severely impact cybersecurity threat detection capabilities. When a model underfits, it means the algorithm is too basic or constrained to learn the complex relationships that exist in the training data. The model makes overly simplistic assumptions about the data patterns. This visualization shows 3 different model fitting scenarios. The left plot demonstrates underfitting, where the straight red line is too simple to capture the curved pattern in the data points. The model misses important relationships. In contrast, the middle plot shows appropriate fitting where the model captures the underlying pattern without being overly complex. The right plot shows overfitting, where the model is too complex and follows every data point too closely. In cybersecurity applications, underfitting can be particularly dangerous because it reduces the system's ability to detect sophisticated threats and attack patterns. An underfitted cybersecurity model might miss complex attack patterns, fail to detect sophisticated threats, reduce overall detection accuracy, and create dangerous security vulnerabilities in the system. The key to effective threat detection lies in finding the right balance between model complexity and generalization ability. Balancing between underfitting and overfitting is critical for effective threat detection. We need to find the sweet spot where the model is complex enough to capture important patterns, but not so complex that it fails to generalize to new threats. Understanding and preventing underfitting ensures that cybersecurity systems can effectively identify and respond to both known and emerging threats, maintaining robust protection for digital assets. Before we can train AI models for cybersecurity, we must first prepare our data through pre-processing. Raw security data is often messy, incomplete, and unsuitable for machine learning algorithms. Here's an example of raw security log data. Notice how it contains various formats, potential errors, and information that may not be directly useful for our AI models. Data preprocessing involves 4 key components: data cleaning, data integration, data transformation, and data reduction. Each step prepares our raw data for effective machine learning. Data cleaning is the first crucial step. We remove noise, handle missing values, eliminate duplicates, and correct errors in our security logs. Data transformation converts our cleaned data into formats suitable for machine learning. This includes normalizing values, encoding categorical variables, and standardizing timestamps. Feature engineering is the art of creating meaningful inputs for our AI models. We derive new variables like average login times, failed attempt rates, and network packet statistics that help models detect security threats. This pre-processing pipeline fits into the broader machine learning workflow. Clean, transformed data with engineered features leads to better model performance and more accurate threat detection. Effective data pre-processing is essential for successful AI in cybersecurity. By cleaning noise, transforming formats, and engineering meaningful features, we enable our models to detect threats more accurately and respond more effectively to cyber attacks. In machine learning, we start with a complete dataset containing all our available data samples. However, we cannot use all this data in the same way. Data splitting is a fundamental pre-processing step where we divide our dataset into separate portions for different purposes. This separation is crucial for properly evaluating how well our model will perform. The most common approach is to split the data into 2 main sets, a training set and a testing set. Typically, we use about 70 to 80% of the data for training. The remaining 20 to 30% becomes our testing set. This portion of data is kept completely separate and will only be used to evaluate our trained model. The training set is used to teach our machine learning model. The model learns patterns, relationships, and rules from this data during the training process. The testing set serves a completely different purpose. It contains data that the model has never seen before, allowing us to evaluate how well the model generalizes to new information. This separation is crucial because it prevents overfitting and gives us an honest assessment of model performance. Let's look at a visual representation of this concept. As shown in this diagram, the complete data set is divided into training data, typically 75%, and test data, usually 25%. This split ensures we can train our model effectively while maintaining an unbiased way to measure its performance. The key principle is that the testing data must remain completely unseen during training. This separation allows us to measure how well our model will perform on new real-world data, which is the ultimate goal of machine learning. Supervised learning provides a powerful approach for detecting network intrusions by learning from labeled examples of normal and malicious network traffic. Network traffic flows continuously between devices and servers. Each connection generates data packets that contain information about the communication patterns, protocols used, and data transfer characteristics. To train a supervised learning model, we need labeled training data. Security experts analyze network traffic samples and classify them as either normal, legitimate activity or malicious intrusion attempts. The supervised learning algorithm analyzes these labeled examples to identify patterns that distinguish normal traffic from intrusion attempts. It learns to recognize characteristics like unusual port usage, suspicious connection patterns, and known attack signatures. Let's see how this works in practice with a real-world example. When new network traffic arrives, the trained model analyzes its characteristics and classifies it as either normal activity or a potential intrusion. The supervised learning model recognizes this distributed denial-of-service attack pattern because it has learned from similar labeled examples during training. It can identify the characteristic high-volume traffic from multiple sources targeting a single server. The model outputs a classification result along with a confidence score. Security teams can then take immediate action to block the malicious traffic and protect their systems from the detected intrusion attempt. This supervised learning approach enables automated, real-time intrusion detection that can identify known attack patterns with high accuracy, providing crucial protection for network security systems. Anomaly detection with unsupervised learning is a powerful approach for identifying unknown cyber threats. Unlike supervised learning, this method doesn't require labeled examples of attacks to detect suspicious behavior. In network security, normal traffic follows predictable patterns. Users access familiar websites, applications communicate on expected ports, and data flows follow established routes. Unsupervised learning algorithms can identify these normal patterns without being explicitly told what constitutes normal behavior. When anomalous behavior occurs, such as unusual data transfers, connections to suspicious IP addresses, or unexpected protocol usage, these activities stand out as outliers from the normal patterns. This is how zero-day exploits and novel attack methods can be detected. Zero-day exploits represent one of the greatest challenges in cybersecurity. These are attacks that exploit previously unknown vulnerabilities, meaning there are no existing signatures or rules to detect them. Traditional signature-based detection systems are completely blind to these threats. Unsupervised learning algorithms like clustering can automatically group network activities into patterns of normal behavior. The algorithm identifies these clusters without being told what constitutes normal or abnormal activity. Any activity that falls outside these established clusters is flagged as anomalous. This approach can detect completely new types of attacks, including zero-day exploits, because it focuses on deviation from normal patterns rather than matching known attack signatures. Advanced anomaly detection systems use sophisticated mathematical techniques like tensor decomposition to analyze complex network patterns. These methods can identify subtle anomalies in network flows, connection patterns, and data transfers that might indicate advanced persistent threats or zero-day exploits. Anomaly detection with unsupervised learning provides three critical advantages for cybersecurity. First, it can detect completely unknown threats without prior examples. Second, it requires no labeled training data, making it practical to deploy. Third, it continuously adapts to new attack patterns, providing robust protection against evolving cyber threats. Reinforcement learning enables cybersecurity systems to create adaptive defenses that learn and improve in real time. Unlike traditional static security measures, these systems continuously optimize their responses based on the outcomes of their defensive actions. An adaptive defense system consists of an AI agent that monitors network activity and responds to various cyber threats. The system must make decisions about how to defend against attacks while learning from each interaction. The reinforcement learning process follows a continuous cycle. The AI agent observes the current state of the network, takes a defensive action, receives feedback about the effectiveness of that action, and then learns to improve future decisions. This cycle repeats continuously, allowing the AI system to adapt its defensive strategies based on real-world outcomes. Each successful defense increases the reward, while failed defenses provide negative feedback, guiding the system toward more effective responses. Let's examine a practical cybersecurity scenario. Consider an AI system defending against different types of network intrusions. The system must learn which defensive actions work best for each type of attack. Modern adaptive security architectures implement these reinforcement learning principles across multiple layers of defense. They provide comprehensive protection through prevention, detection, response, and prediction capabilities. The ultimate goal is sustained cyber resilience. This requires a continuous cycle of assessment, mitigation, recovery, and risk transfer. Organizations become active participants in managing risk through data-informed decision-making. Reinforcement learning transforms cybersecurity from reactive to proactive defense. By continuously learning from each interaction, AI systems develop increasingly sophisticated defensive strategies, creating adaptive security that evolves with emerging threats and maintains organizational resilience. The convergence of artificial intelligence and cybersecurity represents one of the most significant technological transformations of our time. These two critical fields are merging to create powerful new approaches to digital protection. AI brings three revolutionary capabilities to cybersecurity. First, it can analyze vast datasets, processing millions of security events and network logs in real time, something impossible for human analysts alone. Second, AI excels at detecting anomalies by identifying unusual patterns and suspicious behaviors automatically, catching threats that traditional rule-based systems might miss. Third, AI can automate incident response, executing immediate countermeasures without waiting for human intervention, dramatically reducing response times from hours to seconds. Here we see a practical example of AI-powered anomaly detection. Data from key performance indicators, system logs, and network traces feeds into machine learning models that continuously analyze patterns and automatically generate alerts when anomalies are detected. This convergence is revolutionizing cybersecurity operations. Traditional multi-tiered support processes are being enhanced with AI automation, enabling faster threat detection, automated incident handling, predictive threat intelligence, and significantly reduced human workload and errors. Organizations worldwide are adopting AI-powered cybersecurity solutions to protect their digital assets more effectively than ever before. This technological convergence represents a fundamental shift in how we approach digital security in the modern era. Artificial intelligence in cybersecurity represents a true double-edged sword. While AI provides powerful defensive capabilities, it simultaneously enables more sophisticated and dangerous attacks. On the defensive side, AI dramatically enhances threat detection capabilities. AI systems can analyze vast amounts of network data in real time, identifying anomalies and potential threats that would be impossible for human analysts to detect manually. However, the same AI technologies that strengthen our defenses are being weaponized by cybercriminals. AI-powered attacks are becoming increasingly sophisticated, using machine learning to adapt and evolve in real time. This creates an escalating arms race between defensive and offensive AI systems. Cybersecurity experts predict that the future of digital security will be defined by this ongoing battle of AI versus AI. This AI arms race represents a fundamental shift in cybersecurity. Organizations must not only implement AI-powered defenses, but also prepare for increasingly intelligent and adaptive threats. The battle between artificial intelligences will define the future of digital security. While AI brings powerful capabilities to cybersecurity, it also introduces significant challenges and risks that organizations must carefully navigate. First, cybercriminals are now using AI to create sophisticated malware. AI-powered malware can change its code structure to avoid detection, making it extremely difficult for traditional security systems to identify. Deepfake technology represents another major threat. AI-generated deepfakes are increasingly used in social engineering attacks, fraud schemes, and misinformation campaigns to deceive victims. Large language model poisoning occurs when attackers manipulate training data or inference processes to embed malicious outputs. Additionally, over-reliance on AI can create a false sense of security and introduce new vulnerabilities. Ethical concerns and transparency issues pose significant challenges. AI systems in cybersecurity often operate as black boxes, making it difficult to understand their decision-making processes and ensure accountability. Data quality and privacy represent major concerns, with 84% of cybersecurity stakeholders worried about these issues when training AI for security applications. Organizations struggle with data minimization, anonymization, and regulatory compliance. Integration with legacy systems presents substantial challenges, with 65% of organizations reporting difficulties. These systems often lack modern APIs, documentation, and security features needed for AI integration. Perhaps most concerning is the preparedness gap. Only 45% of cybersecurity professionals feel prepared for AI-powered cyber threats, while 93% of security leaders expect daily AI attacks by 2025. These challenges highlight the complex landscape organizations face when implementing AI in cybersecurity. Success requires careful planning, ongoing vigilance, and a balanced approach that leverages AI's benefits while mitigating its risks. We've explored the fundamental AI concepts that power modern cybersecurity systems. These core building blocks work together to create intelligent security solutions that can adapt, learn, and protect against evolving threats. The three main types of machine learning each serve unique roles in cybersecurity. Supervised learning classifies known threats, unsupervised learning discovers unknown patterns, and reinforcement learning adapts defenses dynamically. Different algorithms excel at different cybersecurity tasks. This comparison shows how neural networks, decision trees, clustering, and regression each have unique strengths for computational speed, ease of use, and specific security applications. These fundamental concepts lead us to neural networks, interconnected layers of artificial neurons that can learn complex patterns. Deep learning, built on these neural networks, represents the next evolution in AI-powered cybersecurity. These AI concepts don't work in isolation. Data processing feeds machine learning algorithms, which enable pattern recognition, leading to effective threat detection and adaptive responses. Together, they form the foundation of modern cybersecurity. Understanding these core AI concepts prepares you for the next level, deep learning. Neural networks with multiple layers can learn even more complex patterns and provide more sophisticated cybersecurity solutions. Thank you for joining us on this journey through the core AI concepts in cybersecurity. You now have the foundational knowledge to understand how machine learning, algorithms, and data processing work together to protect our digital world.